Hi guys, in this video we're going to take a quick look at the answers and how we arrive at the answers in the chemistry diagnostic test. You can see that we've got all the questions to the test here. I haven't actually written the A, B, C, D options, but we'll go through them when we go through the answers. So A was how many moles of hydrogen atoms are contained within a mole of this NH4 2H-PO4, we call this ammonium hydrogen phosphate. Okay, so let's have a look at the answers to this. We've got this ammonium HPO4, and it says how many moles of hydrogen atoms are contained within 1 mole of this. And it's literally just a case of counting the number of hydrogen atoms in this ammonium monophosphate, this ammonium hydrogen phosphate. And we see we've got 4 times 2, so that's 8 hydrogens there. And then we've got this extra one there. So the answer to this was 9 moles of hydrogen atoms. That was option D. B asks us to write or look at an equation, and when the equation is properly balanced, how many moles of oxygen will there be? So in effect, what we've got to do then, we've got to balance this equation, and once balanced, how many moles of oxygen we're going to be present. So we've got to balance it. It's a combustion equation where we're burning a hydrocarbon in oxygen. And again, it's what we call a complete combustion because we produce carbon dioxide. And water, incomplete combustion, would contain carbon monoxide or carbon with water. Very simply, how we do this is the number of carbons in your thing that you're burning will equal the number of carbon dioxides that you form. So in this case, that'll be a 3. The number of hydrogens in whatever you're burning, well, you'll then have half that number of waters, so you're going to have a 4. And then we simply add up the number of oxygens on the product side. Well, you can see there we've got 6 oxygens there, 4 oxygens there, so we've got a total of 10 oxygens. Therefore, we need 10 oxygens on this side. So we need to put a 5, because obviously 5 times 2 is equal to 10. Let's have a look at part C. And part C then asks us, and it's asking us, what is the relative molecular mass, the MR, of propene? And you're given the ARs in the question. So we've got C3H6, and it tells you that the AR of carbon is 12, AR of hydrogen is 1. So we simply just do 3 times 12, got 3 lots of carbon, plus 6 times 1, which is obviously 36, plus 6, which is equal to 42. And that was answer B. So 42 will be my answer there. Moving on to part D, or question 4. Part D says, or question 4 is, how many moles of CO2 are present in 220 or 0.220 grams? So we need to work out moles. We need an equation for moles. So moles, we should be aware, moles is the mass divided by the MR. And this is a standard equation. So if you know any 2 of these, you can work out the third. Sometimes you might have to work out mass, and mass would be MR times moles. In this case, we've got to work out moles. We're given a mass, it's 0.220 grams. And we need to divide that by the MR of carbon dioxide. And you're given the ARs of CO2. So carbon is 12, oxygen is 16. So it's 1 times 12 plus 2 times 16. When you add them two together, you get 44. And 0.22 over 44 is 0.005 of a mole. And that is answer B. Moving on swiftly to question 5, or part E. It then asks us, which of the following equation represents the equilibrium equation for the following reaction? So you've got this reaction here, phosphoric acid reacts with calcium hydroxide to produce calcium phosphate and water. It's a neutralisation reaction. So let's just write the equation out. 2HPO, or 2H3PO4 plus 3 calcium hydroxides. And again, you probably should be aware of why these have got that particular formula in terms of the charge on the ions and making the charges balance. So we've got there is my calcium phosphate, and we've got 6 H2Os. So that is my equation. This is an equilibrium. This is my equation. It's an equilibrium reaction. What that means is that when you react these two, the reaction is reversible. And at a certain point in time, the forward reaction will equal the rate of the backward reaction. So as much product is formed as there is reactants. That will mean then the concentrations of the reactants and the products will remain constant. That's what is occurring when a reaction is in equilibrium. Forward and backward reactions occur at the same rate. Concentration of these remain constant. And therefore, at any particular time, with a reaction which is reversible, you will have a fixed ratio of reactants and products. So you've got an equilibrium mixture of all these things with a fixed ratio of reactants and products. And that ratio can be expressed as a constant. It's called an equilibrium constant, and it's fixed for any reaction at a particular temperature. And at the top line is always the products. And we use square brackets to represent concentration. And it's the concentration then of the calcium phosphate. And that is raised to the power of whatever number is in front. And here it's basically a 1. So it's raised to the power 1. And anything raised to the power 1 is just the same as the number itself. We've got the water. And that's raised to the power whatever the number in front. And the number in front is a 6. So that's raised to the power 6. And that's always then divided by the concentration of the reactants. So we've got our H3PO4. Again, the number in front of that is a 2. So that's squared. And then I'm sure you know what's coming then. Calcium hydroxide raised to the power 3. Now, these equilibrium constants are important when we come to look at acid-base chemistry and looking at the dissociation of weak acids. So this equilibrium, these rules of equilibrium, where we've got to divide products over reactants, is something that will come up in acid-base chemistry. Question 6, or part F, an equilibrium constant of 1 times 10 to the minus 4 for the reaction means the reaction is what? Well, if you've got an equilibrium constant which is low, less than 1, it indicates that you've got a bigger number here compared to here. So equilibrium constants which are quite low have basically got higher concentrations of reactants. Equilibrium constants which are high indicates we've got a lot of this, which is more products. So F would mean that you've got a low equilibrium constant, which it is. It's 1 times 10 to the minus 4, which means that you've got very, or small, I would put down low amounts of products at equilibrium. And that there matches answer C, one which is unfavourable, as in unfavourable in forming products, and therefore doesn't have much product at equilibrium. And again, you should be able to visualise that. A low number means this is going to be a low number for K means that this is going to be high. That's a high concentration of reactants. Therefore, the equilibrium has got more. The equilibrium mixture has got a lot more reactants in there. Okay, question 7 or G. It says how many grams of sodium hydroxide are needed to make 100 millilitres of a 0.2 moles per litre solution. So we're looking at this question here. How many grams of sodium hydroxide are needed to make 100 millilitres of a 0.2 litre solution? Just some background. A milliliter is the same as a centimetre cubed. A litre is the same as a decimetre cubed. So you may have come across these terms more commonly. These are interchangeable. So we've got 100 millilitres or 100 centimetres cubed. And it's got a concentration of 0.2 moles per litre. And we need to work out, the first thing you would need to do in a question like this is work out the number of moles that we've got in that solution. And moles is equal to the concentration times the volume. So in this case, moles is going to be equal to 0.2 multiplied. Now the issue is we must make sure that these units are the same. So we've got to convert this into litres. There are 1,000 millilitres in a litre. So that means that if I'm going to convert this millilitres to litres, I need to divide this by 1,000, and that converts that into millilitres. That gives you 0.02 moles. So that's how many moles, how much stuff, how much sodium hydroxide I've actually got in there. We now need to work out the mass of this sodium hydroxide that's needed to make this solution with that volume and that concentration. And the next little bit you do then is work out the mass. And mass is the MR times the moles. The MR of sodium hydroxide, well, that is 23. This is 16. And this is equal to 1. So if we add them up, 1 sodium, 1 oxygen, 1 hydrogen, we get 40 for the MR times 0.02. And that there gives me the answer of 0.8 grams, which was answer B. So let's move on to question 8. And question 8 or H is here. It says which half equation correctly represents a reduction. You're given certain options, 4 options. What I would say is that remember that reduction and oxidation is explained in terms of electrons, and half equations would represent either the oxidation process or the reduction process, and it's asking which of these half equations represents reduction. Now, you should be aware of the term oil rig. So oxidation is loss of electrons, reduction is gain. So if we're looking at a gain of electrons, the electron should be on the left-hand side of the equation. That's the first thing. And there are 2 equations where the electrons are on the left. The first one, which was option A, is Fe3 plus 3 electrons going to Fe. And the second one was Fe plus 3 electrons going to Fe3 plus. Now, an equation has to balance in terms of atoms and charge, and I'm hoping you can see that this bottom equation here does not, because I've got an overall charge of -3 on this side, but an overall charge of +3 on the right-hand side. This equation has got no charge because the 3 pluses cancel by the 3 minus, and this side has no charge as well. So the correct answer was this one. So that was the correct answer for question 8. Okay, Part I, or question 9, it says, which is the pH of a strong acid solution of HCl with a concentration of 0.00001 moles per litre? And you're given the equation for pH. First thing to appreciate is really that HCl is a strong acid, and as such fully dissociates in solution to produce hydrogen ions and chloride ions. And what we're saying then is, for every mole of this that you've got, if I had 1 mole of this HCl, 1 mole of HCl forms 1 mole of hydrogen ions. But what I have got is actually 0.00001 moles. And therefore, for every mole of hydrochloric acid, I form a mole of hydrogen ions, so I'm going to have 0.00001 moles of H+. That's only true for strong acids. If it's a weak acid, we have an equilibrium mixture, and the concentration of the acid does not equal the concentration of hydrogen ions. So we use an equation then. pH then is equal to minus log the hydrogen ion concentration, which is this. And that then is 0.00001. That gives you, when you type that into your calculator, that would give you a pH of 5. You'll cover acid-base chemistry in a lot more depth in specific lectures on acids and bases. Okay, part J, or question 10, which measurement definitely contains 3 significant figures? So that's what part J said. Or question 10, we're looking at this. Which measurement contains 3 significant figures? And we're given 4 options. We're given 0.08, or not, 0.08, 0.080, 800, and 8.08. So which of those definitely contains 3 significant figures? Well, straight away, this one, you should be able to see, contains 1 significant figure, and the significant figure is this 8. And we can see that this one here, well, this is incorrect. This contains 2 significant figures. This one here could, this one here could be 3 significant figures. However, it could also be 1 or 2 significant figures. We don't know. So this, we just don't know. It could be 1 significant figure. It could be 2 significant figures. Okay? So, for example, if you had, for example, 802 to 2 significant figures, the answer would be 800. If you want to say 831 to 1 significant figure, the answer would be 800. But it could be that this is exactly 800 to 3 significant figures. So therefore, the correct answer to this question is actually this one. This is my answer to 3 significant figures. Question 11, or part K, on my little questions here, is which element's ionic radius is smaller than the atomic radius? And you're given 4 options. You are given an option of nitrogen, sodium is your first one. Sodium, nitrogen, neon, and sulfur. And it's saying which element's ionic radius is smaller than the atomic radius. So we've got to form an ion. And we've got to think what happens when these atoms forms ions. So when sodium forms an ion, it forms a positive ion. Now, nitrogen, when it forms an ion, would actually form an N3- ion. Neon doesn't form ions, so it doesn't really have an ionic radius. So we can kind of rule that out straight away. Sulfur, you should be aware, usually forms 2- ions. Again, they're trying to achieve this full out shell or stable noble gas configuration. So we can do this in kind of GCSE style. When sodium loses its electron, it goes from 281 to 28. Nitrogen goes from 25 to 28, and sulfur goes from 286 to 288. So which ionic radius is smaller? And hopefully you can see that in sodium forming an ion is actually going to lose an electron from the third shell, and now it's only got 2 shells of electrons. So what we've got here is sodium has got 11 protons. Still got 11 protons, but it's got 1 less electron, so it pulls, the attraction for the protons to the electron is greater, so it basically pulls the electrons closer to itself. With nitrogen, you've got here the 7 electrons, you're going to gain 3, and again in both cases, nitrogen's got 7 pluses, but these 7 pluses don't have as great a attraction for the 10 electrons as they do the 7, so they're going to kind of make this a bigger atom. Similar principle here. So negative ions are always going to be bigger than the atom that they've been derived from. Positive ions are going to be smaller than the atom that they've been sort of derived from. L, or question 12, says the reaction represented here is an example of what? And you've got substitution, addition, esterification, and fermentation. Substitution, we're swapping one atom for another. So it's not that. This is actually here, this is an addition reaction. Addition reaction, 2 things add together to form one product. So the answer there would be addition. And esterification is where we form an ester. And that is when we form this functional group. And again, this can be formed in various ways, but esterification is when this functional group is formed. Fermentation is obviously glucose reacting to form ethanol and carbon dioxide. So this would be an example of fermentation. Okay, so esterification forms this. Fermentation is an equation where you've got sort of a glucose anaerobically respiring to form ethanol and carbon dioxide, and the substitution would be where one atom is swapped for another. So we're going to go on to M now, or question 13. It says, which compounds are isomers? That's what we're saying. We're given 4 options. Which compounds are isomers? And the options we're given is propan-1-ol and propan-2-ol. And that would be my correct answer very quickly, because what we've got here is an example of a position isomer. It's a type of chain or type of chain isomerism. So that's propan-1-ol, and propan-2-ol is simply where the OH is in a different position on the carbon chain. So it was called a position isomer. Methanoic and ethanoic acid, which was your other option. Ethanoic acid, well, methanoic acid, for example, is, be aware that an isomer, they must have the same molecular formula. Just to go back, an isomer must have the same molecular formula. So propan-1-ol and propan-2-ol are both C3. You can see there, H1, 2, 3, 4, 5, 6, 7, 8, O, C3H8O. Okay, so that's propan-1-ol and propan-2-ol. Both got the formula C3H8O. Methanoic acid and ethanoic acid. Well, methanoic acid is HCOOH, and ethanoic acid is CH3COOH. So obviously that is incorrect. Methanol and methanal. Well, methanol is CH3OH. Methanal is HCHO. So obviously different molecular formula. Ethane and ethanol. Well, I'm sure you know ethane is C2H4. ethanol is CH3, CH2OH. So isomer has to have the same molecular formula, and that therefore is going to be these two. Okay, moving on to question 14, or part N, if you like. If we look at my sheet here. It then says, in which pair of hydrocarbons does each compound contain only one double bond per molecule? Well, if a compound's only got one double bond per molecule, it's got a general formula CnH2n plus, well, it's literally that, it's just CnH2n. So we're looking for where the number of hydrogens is double the number of carbons. So part A is C2H2 and C2H6. Well, what you've got there is this would give you ethine, which has got a triple bond, and obviously ethane is, and I'm not going to put the hydrogens in, will be just have no double bonds. It's saturated. Obviously, we can rule out B because it's not got a double bond. It's this compound here. The answer is C, C4H8, C2H4. It's very quickly. This would be an example of a molecule which would be C4H8. It could be but1-ene or but2-ene. And C2H4 is ethene. So you can see that both species have got one double bond. C6H6, to just give you some context, is probably, well, it's almost certainly a benzene ring. And C7H8 is likely to be something like this. Probably something like methyl benzene. Okay, so the answer there would be C. The correct answer then would be these two here. They've both only got one double bond per molecule. Question 15, or part LMNO. We're on O now. Which of the following alkanes would have the highest boiling point? The boiling point of any substance is due to the forces between the atoms or the molecules. In this case, we're looking at simple molecular structures. So simple molecular structures, well, it's going to be to do the intermolecular forces. Obviously, we've got an ionic bond, we've got a giant ionic, and that's due to the attraction of the ions. If we've got a giant covalent like diamond or graphite, that's due to the strength of the covalent bonds. But here, and like in most drug molecules, we've got simple molecular structures. And that there is to do with the intermolecular forces. Now, what you've got there is 4 different alkanes. So they're going to be just van der Waals forces. And when we're looking at van der Waals forces, the van der Waals force is affected by one of two things: the number of electrons in the molecule. Now you can see here that they're all isomers. They've all got the same number of electrons, the same mass. The other thing which influences it then is surface area. The bigger the surface area, the more points of contact between the molecule and the stronger the van der Waals force is going to be. So if you've got, for example, something which is not branched, like this, and let's just count 1, 2, 3, 4, 5, 6. That's going to have a higher boiling point than something like this, which is, again, let's call it 1, 2, 3, 4, 5, and let's just add another one here. So something like this. These would be isomers with the same number of electrons, but because this has got a bigger surface area, there's more points of contact, and therefore this would have stronger intermolecular forces. So thinking about points of contact, again, if you've got another one here, think about all the different, the points of contact here are greater than if we had another one of these. next to each other. So think about flat sheets of paper are going to stick together more than screwed up pieces of paper because they can touch each other more. And that's the idea of these van der Waals forces. Van der Waals forces will increase with the number of electrons in the molecule or surface area. So branched alkanes will have lower boiling points than straight chained alkanes. Okay, P is which of the following compounds has the highest boiling point? Ethane, chloroethane, ethanol or ethanal. Again, it's through the intermolecular forces. So ethane, that will be simply van der Waals forces, the weakest intermolecular force. Chloroethane, that would be dipole-dipole forces. And ethanol, well, they would form hydrogen bonding. And ethanal would also be dipole-dipole forces as well. So you've got to think then, they've got similar mass. So which one's going to have the strong? Remember, generally, if you've got a massive big molecule, it'll have lots of electrons. That's normally going to have a high boiling point. But all these four are going to have similar, not the same, but very similar masses. And therefore, we're going to look at the one which has got the strongest intermolecular forces. Hydrogen bonding, you should be aware, is the strongest intermolecular force if they've got similar numbers of electrons. So your answer should have been ethanol. Hydrogen bonding, remember, occurs when you've got this hydrogen bonded to a very electronegative atom, O, N or F. And remember that the hydrogen then can attract the lone pair of an oxygen of a neighbouring molecule. So that there would be your hydrogen bond, the strongest intermolecular force. Q, or question 17, that asks us formation of two products from a single reactant molecule. That is known as an elimination reaction. So when you eliminate something, and a very simple example would be something like if you've got ethanol, well, I'll put the hydrogens in. An elimination reaction is when, for example, a dehydration of ethanol, you lose H2O and you form an alkene. So that would be an example of an elimination reaction. An elimination, formation of two product molecules from a single reactant. So that would be called an elimination. Oxidation is, well, that's not going to do that. It's not going to form two product molecules from a single reactant molecule. Propagation, no, it's not going to be that. Propagation is a step within a free radical reaction, and substitution is swapping one atom for another. Okay, question 18, or part R. So have a look at part R. It says free radicals are not produced in, and you've got options of initiation, propagation, termination, or all above. Very quickly, an initiation step will form free radicals. So that, for example, would be where you break this bond homolytically, and one electron goes to one chlorine, one electron goes to another, and that there would be an initiation. So again, if you're struggling with that, look at my YouTube video on substitution reactions. Propagation step would be, for example, where propagation means to grow. So an example of a propagation step would be something like this, and you get, again, radical would be formed. So that's one propagation. Another propagation step would be where this radical reacts with another chlorine molecule. You get, so this is an example of propagation steps. So these are propagation. Propagation means to grow. And termination is where any two radicals combine. So, for example, could be these two, any two radicals combine to give a stable molecule. So the answer there would be termination step. So termination steps, which is this, is the step which does not produce free radicals, because we can see radicals are produced in initiation and radicals are produced in propagation as well. Electron pair acceptor is the next one, which is part S. So it says an electron pair acceptor is termed as, well, we've got a nucleophile is actually an electron pair donor. A carbocation is, for example, a carbon which has got a positive charge, something like this, and also an anion is something like any sort of negatively charged species. So the answer would be an electrophile. Probably a better definition of electrophile is an electron deficient species. And these electron deficient species will usually accept a pair of electrons. So if you've, for example, got an electron deficient carbon, for example, then that usually will accept a pair of electrons from a nucleophile. And you may have seen sort of these mechanisms before. So, for example, if that's an X, a halogen. So that there is your electrophilic centre, and it's sort of accepting this pair of electrons. Okay, next is part T, and it says which compound is not a carboxylic acid. Carboxylic acids have to have this functionality, and we can see that in the first one we've got CH3COOH, so that ticks that box. We've got that functionality there. Part B has got the following. Let's just do it correct. So we've got that as a sort of a skeletal formula. Again, it's still got this COOH functionality, so that is correct. Part C is this molecule, and you can see here that the you've got a C double bond O, but then you've got this gap, this CH2 group in the way. So actually what you've got there is this is a ketone and an alcohol, because this OH has to be directly bonded to the carbon with the C double bond O. So C would not be a carboxylic acid. E is obviously D, sorry, is just the same as this molecule, but just sort of upside down. So that there, guys, goes through the chemistry diagnostic test very quickly. As I said, I hope that's been okay. There may be some stuff on there that you need to sort of look at again, but if there's any problems, you can simply ask.